to do this. Okay, so the question was number 12. So here's number 12. It asked you to identify the type of compound you have, either molecular or ionic, and if it is going to be an electrolyte or non-electrolyte. So this goes back to that electrolytes activity that I posted online for you. So you guys had to do a lab activity with that. Let's see, just do that. Compounds that are molecular start with a non-metal. So for example, distilled water is water. That starts with a non-metal. Hydrogen's a non-metal. So this is going to be a molecular substance. Sorry, my handwriting's so bad on here. And then molecular substances do not dissociate in solution. So they're always going to be non-electrolytes. Calcium fluoride starts with a metal. If it starts with a metal, it is going to be an ionic compound. Ionic compounds do dissociate in solution, and they are going to be electrolytes. Sorry, guys, you hear my dog. I think the UPS guy dropped something off here. Sodium chloride starts with a metal. It is going to be ionic. And because it's ionic, it will dissociate in solution, which means it will be an electrolyte. And then sucrose is C12H22O11. This was also a substance we tested. Sucrose is sugar. Starts with a non-metal, and we saw before that it was molecular. And that would make it a non-electrolyte. All right, so I'm going to just kind of start going through things, especially where I've seen people having trouble with problems. Like in number 8, 9, 10, and 11, when I was grading the solubility worksheet, a lot of people were getting these wrong. As the temperature of a solution increases, solid solubility. So temperature and solids. When you increase the temperature, solids will dissolve more. You can dissolve more of that solid at that given temperature. So solid solubility increases with temperature. Now the opposite is true for gases. As you increase the temperature, so for example, if you increase the temperature of pop, it can hold less gases. That's why warm pop becomes flat, because it's holding less gas substances. So that is a decrease in solubility then. Now, pressure in solids have no effect. Pressure does not affect solids whatsoever. The only thing that pressure affects is gas solubility. So this, again, you can kind of bring back to that idea of pop. When you have a can and it's sealed, the pressure is pushing on that gas in the solution, and it holds the gas in. So more pressure you have, the more gas solubility you're going to have. Now, if you open that can and release the pressure, you're also releasing the gas. You're letting that gas escape. So if you had a decrease in pressure, you'd have a decrease in gas solubility. All right, so let's go to number 13. 13 is dealing with the idea of like dissolves like. Polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes, but polar and nonpolar will not mix. So here it says water is a polar molecule. Vinegar will dissolve in water, whereas oil will not. Based on the given information, identify vinegar and oil as either polar or nonpolar. Well, since vinegar dissolves in water and water is polar, like dissolves like means that vinegar has to be polar. Oil will not dissolve in water. Water is polar, therefore oil must be nonpolar. They are not alike. They will not dissolve in each other. 14 was one in which a lot of people had a hard time with on the supersaturated solutions lab. A lot of people didn't even do the question there for that one. Percent by mass is actually a pretty simple problem. It is going to be the mass of your solute divided by the mass of your solute plus solvent times 100. So for this problem here, your solute is 24 grams. Your solvent is always water. Water is always a solvent. So you're going to have your 24 plus 122 grams there times 100. That comes out to be, for that problem there, 16%. And you need to label your substance sodium chloride. So you have your solute divided by your solute and solvent times 100 for that one. Now for 15, this is dealing with volume. Masses are additive. You can add masses and it's always going to be the same. Law of conservation of masses, it has to be. Solutions are kind of goofy. Like if you mix 50 mils of water and 50 mils of ethanol, it makes 95 milliliters of solution. So that's why I always give you the solution for volume problems. So percent volume is going to be the volume of your solute divided by the volume of your solution times 100. So you don't have to do anything special there. It's just going to be 23 mils divided by your solution of 97 mils times 100. That one there came out to be 24% ethanol. Now, molarity is one in which I've had a lot of people struggle with. Molarity is a pretty simple equation. It's going to be the moles of your solute divided by the liters of your solution. Now, this problem, I give you moles and I give you liters. So this is a pretty straightforward, simple problem. 3.85 moles divided by your 4.3 liters is going to leave you with 0.90. Molarity is represented with a capital M, molar sodium hydroxide. Now, a problem like number 17 involves a little bit more work. To find the molarity in 17, you have to turn grams of sodium chloride into moles of sodium chloride, and you do that using molar mass. Molar mass of sodium chloride is 58.5 grams per 1 mole. And then here you need to divide. I have a lot of people doing some goofy stuff, taking 58.5 divided by 24.5. Remember, you multiply across and divide by the bottom. So 24.5 divided by 58.5 is 0.419 moles. You're going to divide that by liters of solution. 540 milliliters. Divide that by 1,000 is 0.5400 liters. So divide that by 0.5400 liters. That comes out to be 0.776 molar sodium chloride. So molarity is moles divided by liters. If you are given grams, you got to turn those into moles using molar mass. If you're given milliliters, divided by 1,000 to end up with your liters. Number 18. This one, you see the keyword dilute. Whenever you see dilute or stock in solution, you are going to use the equation M1V1 equals M2V2. And then you know which two sets of data go together because they're separated by the word of. So 25 mils of 12 molar hydrochloric acid. This is going to be your V1 and this is going to be your M1. Since the next number is 500 milliliters, that's a volume. So we're going to label that as V2, which means that we don't know M2. So to get M2 by itself, I'm going to divide both sides by V2. And what we end up with then is M2 equals M1 V1 divided by V2. Plug in your values here. We had 12 molar for M1 times 25 mils for V1 divided by 500 milliliters for V2. You have 2 sig figs, 2 sig figs, 3 sig figs, 3 sig figs. So my answer is going to end up with 2 sig figs, which is 0.60 molar hydrochloric acid. That's a really bad looking zero. Well, I don't know if I made that better, but that's what that's supposed to be there. 19, how many grams of potassium hydroxide would be needed to make 4.2 liters of a 1.4 molar potassium hydroxide solution? In order to do this problem, we have to know moles. And the way we find moles is by taking your molarity times your volume times your liters. So I'm going to take my molarity of 1.4 molar, which is moles per liter, and multiply it by my volume, 4.2 liters. When I do that, liters cancel, and I'm left with moles. 1.4 times 4.2 is 5.90 moles. Not zero, sorry, 5.9 moles. Now, my answer is not moles. They're asking me how many grams of potassium hydroxide do I have. So now I need to multiply my moles times the molar mass of potassium hydroxide, which is 56.1 grams. That is going to leave me now with grams. Moles will cancel, and I'm left with grams of potassium hydroxide. You have 2 sig figs, 3 sig figs, so your final answer is going to have 330 grams of potassium hydroxide there. Now, the last type of molarity question you had was like for number 20 there. What is the molarity? Again, you really have to know what molarity is. Molarity is moles divided by liters. So to find the molarity of this solution, I have to know how many moles I have and divide it by liters. Well, I have 500 milliliters of solution. Remember, you divide milliliters by 1,000 to get liters, which is 0.5000 liters then. And it tells you here, each circle represents 0.50 moles. So to find out how many moles I have to count how many circles I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 circles. So I'm going to have 10 circles times 0.5 moles, which leaves me with 5.0 moles there. Now to get my molarity, I have to divide my moles by liters, 0.500 liters. And that comes out to be there 10. Now to represent 10 with 2 sig figs, because I got 2 sig figs on top, 1, 2, 3, 4 on the bottom, I need to put a decimal here to show that I have 2 sig figs. I need to label it with a capital M for molarity, and my substance is HCl. For 21 through 25, really important. Again, I had a lot of people get the types of solutions wrong on the supersaturated solution lab. So there's some key terms, some key ideas here to help you understand whether or not it's saturated, unsaturated, or supersaturated. Whenever you have solute on the bottom of your beaker or your cup or your test tube, that means that the solution is holding the max amount it can and all the extra goes to the bottom. That means it is saturated. Holding the maximum amount of solute is a saturated solution. 22, we talked about electrolytes are always coming from ionic substances. For 23, if it is unsaturated, I can add more solute to solution and it will still dissolve. So the answer here is A. I can add more solute and it will still dissolve. If it is super saturated, and you watched a couple of those videos that I requested that you guys watch, you would have seen this. So when a crystal solute is added to a super saturated solution, that disturbs the solution and it causes it to recrystallize or to precipitate in solution. So those are all the crystals that you see forming within that solution. If I add a crystal solute to a saturated solution, it's already at the maximum amount of solution. It won't hold anymore. It's just going to fall to the bottom. I'm going to go back here for a second and see. I'm going to go through the solubility questions, but I just want to make sure I'm not ignoring you guys and going too fast or anything like that. How are we doing? Any questions for me? If you do, if you just want to type it into the chat bar, you can do that. So if there's something you want me to re-explain or go over. Okay, then I'm going to go back and talk about the solubility questions. All right. So the first question, what mass in grams of sodium chloride can be dissolved in 100 grams of water at 0 Celsius? Whenever I give you a temperature, you have to go to your graph. So I'm going to go to my graph and find 0 degrees Celsius, which is here. And I'm going to find sodium chloride, and that hits right about there. This is an approximate answer. I would say it's about 37 grams of sodium chloride there. If you wrote 38, you wouldn't be wrong. Like I said, these are all approximate values here. Same thing then for number 27. What mass in grams of potassium nitrate can be dissolved in 100 grams of water at 90 degrees Celsius? So I go to the graph, find 90 degrees Celsius, which is right here. Go up and see where that intersects, and it intersects right there, which is at 200 grams. So at 90 degrees Celsius, you can hold approximately 200 grams of potassium nitrate. Now for 28, when we did the solubility curves class practice, I talked about how to do these kinds of problems. I said, put in data points. Sorry, I'm erasing this stuff so it doesn't get confusing. Put in data points and see where that data point is in location relative to the actual curve. So we have 50 grams of potassium nitrate at 34 Celsius. So I'm going to find 50 grams, find 34 Celsius. So here's 30. 34 is approximately right there. So I'm going to put a data point there. 20 Celsius and 50 grams would be right here. And 75 Celsius. So here's 70, 75 is halfway, and 50 grams is right here. Now at 34 Celsius, I am on the KNO3 line. Because I'm on the line, I'm holding the maximum amount of solute that can be held. Therefore, it is a saturated solution. At 20 Celsius, I am above the line. You can see the line is red there. I am above that line. When you are above the line and everything is dissolved, it's holding more than the max than it should. Therefore, it is a supersaturated solution. And at 75 Celsius, I was here. I'm way below that line. When you're under the line, that means I can add a lot more solute. I can add all this extra solute and still have it dissolve. Therefore, it is an unsaturated solution. So whenever you're doing those types of problems, see where your data point goes in reference to that line. On the line is saturated, below the line is unsaturated. Just kidding. Below the line is unsaturated, and above the line is going to make it supersaturated. All right, so 29, 30, 31 are the calculation type problems. When we did our practice, we talked about key terms. Here we see the key term precipitate, which means it is a subtraction problem. You have to look at your solubility at those given temperatures and subtract what those values are. So at 80 degrees Celsius, my substance is KNO3. So I'll find 80, and then KNO3 intersects with 80 right about there. maybe 169, 168 grams. My key says 169, but I'm going to use 168 here. At 15 Celsius, KNO3, so here's 10, 15 is halfway. I'm right about here, which I would say, I don't know, 25 grams or so. So about halfway. So 168 grams minus 25 grams there comes out to approximately be 143 grams of potassium nitrate. So keyword was precipitate, which means subtraction problem. You figure out your solubilities at those two temperatures, subtract them. That's how much is going to precipitate back out of solution. For number 30, here our key terms is how many more grams. When you see that, that is also going to be a subtraction problem. Whenever I give you a temperature, you go to the graph. So I go to my graph at 90 degrees Celsius. My substance is KNO3, and I can hold 200 grams. So at 90 Celsius, I can hold 200 grams of potassium nitrate. How many more grams of potassium nitrate must be added to make the solution saturated? Well, I only have 42 grams of potassium nitrate. So 200 minus 42 leaves me with approximately 158 grams of potassium nitrate. So I only had like 42. I needed to add that much more to get it to be a saturated solution. The last problem that we have here is a different amount of water. I mean different amount of water because it's not 100 grams of water. That's what the graph is always showing. We said when you had a different amount of water, you were going to have a proportion type problem. So this is a proportion problem. How much KCl can you dissolve in 360 grams of water? Well, in 100 grams of water at 80 Celsius, so we find 80 Celsius and we find KCl right there. I can hold about 50 grams of potassium chloride. Well, how much could I hold in 360 grams of water? What I need to do here is cross multiply. X times 100, so 100x, equals 50 times 360. And 50 times 360 is 18,000. So divide both sides by 100. And what we get is 180 grams of potassium chloride. That's how many grams that you would have to add to make it a saturated solution in 360 grams of water. I'm just going to slide back up here and see if there's anything else I wanted to address. Normally, vocabulary isn't too bad, especially if you go back to the notes. Everything is in the note slides or your note packet if you filled out your note packet. If I can stress one thing enough is filling out that note packet so you have that as a reference to help you do your homework. So for this next chapter, that's going to be really important, the new one that we start on Wednesday. Last thing is number 6, how do you make a supersaturated solution recrystallize? Initially, it is all dissolved. So if it's supersaturated, it's all dissolved. It looks just like a clear solution. If I add a crystal of the solute, like they did in the lab, then that solution will recrystallize. It will come back out of solution and you will see all the pretty crystals produced there. All right, so I'm going to go back to the meeting and stop presenting.